Okay, so thanks a lot for the invitation. As you mentioned, I am currently based at ETH Zurich. My research focus is really on adaptive and on-site robotics. And previously, I was actually at the ICD Stuttgart. So a lot of the work that I'm going to show today is coming from those two contexts, but mostly from ICD because I was there for about 5 years. And I'm pretty happy to be here to be here virtually because I came to an AEC Hackathon at TU Berlin, and I thought it was a great event to kind of incentivize and disrupt construction, which has been so slow to so resistant to technology, let's say. So I'll start, I think, my presentation with some statistics that we're all familiar with, and that is that the construction industry is among the least digitized when we compare it to healthcare, real estate, transportation. Really, construction has really been very slow to embrace digitalization, and of course also to embrace robotics. So when we think about robotics in construction, we probably are very familiar with the kind of industrial robot arm and the progress that has been made recently. But what's interesting, there's a kind of rich history in Japan already in the 1970s when they were actually very interested in developing construction robotics, but somehow it failed to take off. So it's very kind of important to think about first being aware of the past so that we don't try to repeat things that have already been tried. So already in Japan in the 1970s, because Japan also has an economy where they have a population that was dwindling, they were very interested in construction automation. So one of the early concepts that they had for construction automation was this concept for the single task construction robot. And what didn't really work about these kind of single task construction robots is that they were couldn't take on the diversity of tasks that is kind of implicit in the construction site, where construction workers and people have to do hundreds of tasks, not single individual tasks. And already actually in the 1990s, we already saw CNC controlled robots being programmed. But what was very interesting is that these kind of first initiatives also were really focusing on taking manual work, such as this kind of masonry construction, and automating it for the robot, rather than kind of redesigning systems for the conditions and the possibilities of robotic construction. And then my favorite approach was actually this approach that was developed around 2000, which was basically an attempt to put a factory floor directly on the construction site. So one of the problems that we have in construction, of course, is that building sites are extremely unstructured. So what's very interesting about this approach is that they said, what if we basically build a factory floor, move it upwards, build each kind of level of a building, and use that to kind of automate construction. And of course, that's very limiting as well, because you need this kind of huge factory, and it's going to only be able to produce a kind of standardized profile for your building. So it's not going to offer customizability. So if we kind of move forward to today, to the robots that we're kind of used to being in architecture and construction kind of research environments, we're of course very familiar with the fact that these robots came from a very different context. So here you see the Tesla Motors assembly line, and these kind of robots, these industrial robots, they were really developed to sit on the assembly line, execute the same task over and over and over again with a high degree of speed and precision. So very different from the construction site. And yet we've really appropriated them for construction and for architecture. And on the one hand side, we can say that they present a lot of opportunities for us because they're inherently generic. So they are 6-axis, they can move freely through space, but at the same time, they were developed for another set of conditions. But what's very exciting for us, and why this is a breakthrough about 10 years ago, is that we can develop custom Effectors and tooling and really invent entirely new building systems and processes. So at the ETH, the first robotics lab that really appropriated the industrial robot for architectural use was actually Grammatio and Kohler. And they did that already in 2005. So if we think about that, that's only 15 years ago. And they were the first to really use the robot for very customizable, bespoke production, where they made the most of the kind of digital design environment to design something quite unique, and then use the robot to program and realize that very, very specific design in reality. And one of the first times that actually industrial robots were actually deployed towards large-scale permanent buildings was actually a exhibition hall that was actually done at the ICD, which is at the University of Stuttgart, under the direction of Achim Menges at ICD, and also Professor Knippers, who's at the ITKE. Basically, they used the Landesgartenschau, or the industrial robot, to basically realize this kind of very thin shell interior structure. And here you can, for example, see the kind of computational agent-based framework, which is basically treating each kind of plate as an agent and trying to find a good solution that mediates between fabricatability, but also robotic reachability. And what's very interesting about this early use of the robot in construction is that it really treated the robot in the same way that the robot is being treated on the factory floor. It really treated the robot as a very precise tool that's otherwise quite dumb. So it could mill very precise bespoke joints, but for example, it couldn't handle tasks directly on the construction site. So even though the prefabrication was done with the robot, everything else in the construction pipeline was done very conventionally and very manually. So here you can see kind of an image of the construction process, which is done by hand. And of course, here you can see the kind of final product. So of course, it's a highly beautiful example, but it also had certain kind of limitations, which kind of foregrounded early iterations of how robots have been used for architecture. So I would actually argue that there are kind of two different paradigms of construction. The first is that we think about the world and we think about our building design process as being one where we represent what we're going to build with very high resolution. And we treat those kind of plans and those blueprints as being the source of truth. And we treat at the same time robots, we expect robots to execute those plans with sub-millimeter accuracy. And on the other hand, here's a vision, for example, of Stuttgart 21, which is a famously overdue project. Here we can see that in reality, the construction site is very messy. Materials are unstructured. There's a million things going on at one time. And so can we shift to think about construction instead of this perfect lab-like condition to thinking about how we can develop processes that are more robust, that are capable of being executed in these kind of very robust conditions. So I would argue, for example, that in the first production pipeline that I showed, the Landesgartenschau exhibition hall, there are a few different problems that have ultimately kind of limited the way that we've treated robots in architecture and construction. The first is that we've treated the kind of fabrication pipeline as something highly linear. So we freeze the design and then that's translated directly into the machine control code. But here, the machine has no underlying knowledge about the underlying design logics that were actually implicit in the CAD geometry. So this, for example, would be problematic if all of a sudden something unknown happened and the machine had to kind of react to this scenario. We've also been relying on the ability of wood, for example, to be a highly engineered material. So historically, of course, wood is actually not an isotropic material. We've developed techniques over centuries of years where we take, for example, different layers to produce this kind of highly engineered material. And this is basically a mechanism by which we can control tolerances and control the mechanical properties But we're also, for example, maybe missing out on some opportunities to really use the kind of innate mechanical properties of the materials. In our production pipelines as well, simulation is also a very important thing to think about. So Professor Knippers, who is actually also at the ITKE, he said, until today, well-defined typologies for building structures are used again and again. What cannot be calculated cannot be built. This is very important because some structures that we can conceive of that we cannot calculate or verify, we can't actually build. So there's a huge kind of possible range of structures that could be theoretically robotically built, but because of our kind of conservative building codes, we don't we can't really unlock all of those possibilities. And finally, we have kind of limitations which are operative because of the way that we use our tools. So our BIM models are highly high resolution, very precise, very specific, but there's certain kind of material typologies which might be, for example, flexible during production, which would be very difficult to be represented by our CAD tools. So in a way, our CAD tools are also influencing the way that we're using robotics in architecture and construction. So finally, we have now in this kind of context of Industry 4.0, we have this kind of concept of a cyber-physical system, which is really just a way of saying that you can take physical processes and couple them with back-end kind of digital monitoring, digital processes. And we can ask ourselves, if we really tightly couple these things, what is newly possible for architecture and construction and robotics? So of course, there's several different enabling technologies that are really, really enabling us to really rethink the way that we're using robots. We have network communication, that's at high speed, so we can have multiple processes, sharing data, sharing information. We can make our kind of custom interfaces, we can use augmented reality, and we can, of course, now embed sensors in almost everything that we're doing. It's much cheaper to do so because, of course, not only is computational power, going up exponentially, but the kind of costs associated with embedded sensors, IoT, those kinds of things are simultaneously going down. So simultaneously, we have all of these new kind of technological opportunities, which really enable us to rethink the way we're using robots. Of course, the other problem that is kind of inherent to AEC is this problem of interoperability. So now there are new workflows, there are new kind of environments, visual scripting languages that are really combating interoperability to really unlock a breakthrough on a large scale. And this is maybe enabling us to go from the first paradigm of construction of only operating in the lab environment to transitioning to the second environment, where instead of programming robots with very specific geometric instructions, we can think about programming them with kind of high-level goals. And we can think about using sensors and other adaptive strategies to really sense and react to material inconsistencies, things that we couldn't calculate, or unknown behavior. So this is a kind of shift from many processes being compartmentalized to many processes being integrated. It's also a shift towards process autonomy. So instead of thinking about robots as being dumb machines, we can think about them sensing and reacting to their environment, which is what I'm going to show in one project. And we can also think about how we can leverage digital mechanisms to really enhance and enable collaboration. So for example, in a scenario of human-machine collaboration, can we think about how we can orchestrate kind of a tight collaboration where they can kind of exchange tasks, for example? And can we also think about how, instead of only using materials that are highly engineered, highly predictable, can we also think about other types of materials? So materials that are flexible, materials that are non-standard. Can we kind of expand the design space and develop new robotic processes for these types of materials. So the first project that I'm going to show is a project that kind of attempted to kind of reconsider these plate shell structures that I showed in one of the early examples. So this is from an AECH master's thesis who was in our kind of advanced AECH program at the ICD and ITKE, which is called AECH. It's basically a 2-year advanced master's program, Masters of Science. So basically, Julian developed a kind of iterative workflow where the robot would basically grip the kind of raw material stock. It would mill the stock, it would make a plate, it would also assemble it, then it would scan what it had previously built, and it would update the digital model, all in one kind of iterative loop. So in contrast to the earlier example, where the kind of construction and manual processes were done by hand on site, here we have a kind of a process that could actually be done iteratively, robotically. So of course this has design ramifications because the robot has a very specific reach. So here he's showing what, for example, what kind of shell structure the robot could build if it was actually actively assembling. So this is an important consideration because robots have not been kind of designed to really unlock a lot of design potentials. So in some senses, they're very deterministic. So this was a project that was kind of executed on a similar scale, but instead of taking the kind of plate shell geometry, this project looked at how we can develop new building systems where we really leverage the kind of flexibility of the material during the construction process and use a kind of robotic Effector to really form the material in situ and to produce a kind of very stable composite shell. The concept for this production process was basically that we'd have a Effector, which basically allowed 3 sheets of plywood to be kind of positioned correctly in space. And those sheets of plywood would then be riveted and then filled with a kind of thermal foam. And with each kind of iteration, what was produced previously would then be scanned. So here you see the kind of materials that were produced were kind of part of the kind of sandwich composite. And here you see the kind of Effector that was developed for the process. So the 3 pieces of plywood are kind of connected at the base. Then there's a rotating fork that can reposition itself. So it can basically move in space, kind of supporting the kind of flexible sheets of plywood in position as it moves up. And then those things can be riveted in position. And it basically makes in section a kind of stable plane because you have 2 flexible sheets and then you have one that's kind of undulating back and forth between the 2 layers. So of course there is some spring back. So the question is, how do we handle this, these kind of material effects? So here you can see the students scanning each layer and then, you know, basically updating the kind of machine control code for the next layers. So here's the kind of vision for how it could be built. And then it would be filled with this foam, which for example was just kind of a typical foam that's often used in construction. But in the future, we can think about what kind of bio-based material foams might be kind of good infill material choices that are more sustainable. And here you can see, of course, a live load test. So it's actually a very performative material system. And what I think is very exciting about it is that basically the robot was used as a kind of active formwork. And it's actually an active kind of envelope. So this is something that is always kind of a challenge in digital fabrication. And to me, the final thing is that it really kind of evokes the question, because we're very familiar from the previous project, that these 6-axis robots have very specific design limitations. So how do we imagine the kind of robot and the kinematics that would actually unlock the kind of design potentials of, for example, a kind of shell geometry? So for me, this kind of pointed to a lot of interesting research questions in the future. So also at the ICD and the ITKE, we did some projects on a large scale group that were done in the context of a kind of design studio. So this was in a team of researchers and students. And this project was done actually already starting in 2014. And it was basically a research pavilion where we had industry partners and our kind of core team of students, which were our iTech master students. And we were all investigating this kind of set of research questions. So the material system in this case was actually fiber composites. So fiber composites are a very performative material system that has been kind of engineered from the aerospace and aeronautical industries. But typically on a large scale, you have many different fabrication processes as the ones depicted for both sails, but also for wind turbines that are basically mold-based. So with a mold-based process, you have a mold, and then you can put the material into the mold and somewhat press it into the mold. But what's unfortunate is that you always have this very rigid formwork, and you can only make the same form over and over and over again. So the studio actually began by investigating kind of other precedents in nature that are also kind of fiber-based material processes. So one interesting biological example is this diving bell water spider, which actually traps air underwater and then kind of systematically reinforces the soft pneumatic with fiber. And you can actually remove the kind of pneumatic from the water, and it's actually a very stable compression form after it's gone through this transformative process. So we translated this directly to a kind of concept for fabrication, where we would literally have a kind of soft formwork instead of a rigid formwork, a kind of inflatable formwork, and we'd have the robot at the center, incrementally applying carbon fiber rovings with kind of epoxy resin on the inside till it kind of hardened and cured, and then basically enabled that kind of soft shell to slowly transition to a kind of compression shell. So the first design challenge for this project was really understanding the limitations, for example, of the robot. So we had a robot delivered to us from KUKA. And what's funny is that KUKA is basically each robot has a very specific kinematic reach. And before we got the robot, we actually hadn't studied the reach. So when we got the robot and we were trying to actually simulate some of the paths, we realized that it was actually more of a design challenge than we had anticipated. So this is a kinematic study where we said, what are the kind of different IK configurations when you have a fixed base? So there's actually a few different points along the kinematic chain that you can mirror, which means there's actually 2 times 2 times 2 unique kinematic configurations for any kind of target frame on the end effector. So here you can actually see what the robot can reach if it's trying to stay in one configuration continuously, because you actually can't switch from one configuration to the other mid-path. So for example, we knew that we needed to design something that really stayed within the robotic reach envelope. So here we're just making a kind of very basic physics inflation process, and then we pull back the pneumatic into the kind of reachable envelope of the robot. So here you can see a kind of integrated design process is very important. What I realized kind of later into the project development is that the robot can actually reach more if it knows that it, in certain positions, that it can rotate its application roller. So this is kind of a virtual behavior where the robot is testing, can I reach it? No. If I can't, let me just rotate my arm until I can reach it. And then it kind of stores this value for access later when it's kind of moving in those positions. What's also very different about the kind of design process here is that we basically developed an agent-based system, which is a kind of computational tool where you have an agent which can navigate along a kind of environment, and it can perceive certain things that's in its environment, which can influence its path. So we had a few different kind of data structures that were influencing the robotic motion that could be kind of linked to, for example, structural analysis. You could say, oh, I want the agent to follow these kind of areas of high stress more frequently. Or we could kind of already design some of the kind of fiber bundles, see which ones had the biggest kind of influence on the global buckling stiffness, and then pass those curves into the kind of agent-based behaviors. So in the end, it became a design tool where we were actually developing the kind of logics for this virtual robot in the CAD space to navigate and generate these kind of fiber layouts, really respecting different constraints, but also different inputs. So it became a very kind of open-ended design tool, and you can imagine it could eventually become actually uploaded directly onto the robot brain to enable it to kind of react autonomously. And here you can see that we could generate very quickly a lot of different iterations of kind of viable fiber paths. At the same time, we had to develop a kind of end effector that would really enable us to sense and react to the kind of unknown position of the inflatable. So here you can see an end effector. I'll try and play the video again. That was basically equipped with a load cell, so it knew if it was pressing the membrane, and it knew how much to come off the membrane, for example. And at the same time, it was trying to synchronize how much it was pulling these kind of carbon fiber rovings off of these rollers, synchronizing the degree to which it was extruding with the kind of speed of the robot, and also spraying glue. So here you can see a video. All of these videos, most of them are available on the ICD Vimeo web page, so check them out. You can see the process. So it's extruding. It's also kind of adjusting its path as it's going. It's slightly over extruding because if we accidentally under extruded, you could actually pull off what you had just previously laid. So we could move about 1 to 2 meters per minute. It was a very slow process, but in the end we were able to produce it in a short amount of time because it was just such a lightweight construction system. So here you can see the kind of whole digital workflow, which with each iteration there was the kind of agent-based code, which basically output a kind of rough fiber path. The robot was constantly adjusting for its pressure, and it was updating the kind of motor speed and the spray device at the same time. And here, when we were inside watching the process, for example, we can get all the feedback from the whole system. So we can see what the pressure is. It's telling us if it's too high. And of course, sometimes it's advantageous to have a human in the loop to be aware of the kind of signals that you're getting from everywhere to kind of aid in troubleshooting. So here you can see kind of later in the construction process, after we kind of released, we had this kind of protective tent over the structure. After we moved that, we were about to kind of release the pressure entirely and cut out the openings. And of course, there was a lot of troubleshooting actually during the process. So actually, what we built, we had not pre-designed at all. So actually, during the process, we had to rerun the agent code on almost even a daily basis based on how the construction process is going. So we really can't think about design as being this process where you design something and then you realize it and you try to build something. In some cases, it's very advantageous to kind of be able to adjust and fine-tune things on the fly in response to the real process. And what's also very exciting, and one kind of new area of research, is that we have the ability to actually record the data that we took during construction. So one thing that I noticed is that you can actually prove, based on how much the membrane deflects, that the deflections change from up to 30 millimeters over the course of time. So what that tells us is that the structure itself became very, very stiff, much more stiff with the same load. But the interesting question there is that how do we say if this structure deflects less, how do we know, kind of relate that back to real material properties? So how do we inverse engineer and understand from the kind of data that we're gathering from production? And of course, here we actually load tested it. It was actually up on our campus for up to a whole year, and it took about 560 kg of load. But it was only a 260 kg structure, so this is actually quite interesting. So here you can see the kind of beautiful qualities of the prototype. It enclosed about 40 meters squared. So the last project, actually I'm going to show two more projects very quickly and then wrap up with some final thoughts. This last project was executed in a kind of similar framework as the previous project, in that it was a research studio done with a team of researchers such as myself and a team of students under the guidance of Professor Akim Menges and also Professor Knippers, some other partners, and some industry kind of partners as well. So in this case, the kind of research question became, how do we kind of address this issue of scale? Because in previous robotics projects, for example, the bubble, you saw how kind of limiting the kinematics of the robot can be. So the question was, how do we build with a robot that can really, is not constrained in terms of its mobility? The obvious precedent here is work that has been done at ETH. So already the Frac Tower was done between Matteo Kohler and also Rafael De Andrea, and they built, for example, used the robot to build a kind of styrofoam tower and also a tension active bridge. And here you can see that the large tolerances due to the control of the drone lead to also large kind of spacing between the bricks and between also the tension active structure. So our concept here was not to use the drone as something that would actually need to place the material, but actually merely to use the drone as a kind of vehicle which would enable the material to pass from one robot to the other. So we can still maintain the kind of high payload advantages of the robot, but also really extend its workspace by connecting it to a kind of fully untethered UAV drone. So here you can see the kind of experimental setup. So we actually did this in our lab environment. So you have two different robots standing at two ends of the corridor, and we had the drone moving back and forth with a kind of two sets of landing platforms, and also kind of supporting hardware and, for example, a kind of tension control mechanism. So in this case, the kind of design process was fairly deterministic in that we knew we would make something cylindrical, but it was really about kind of fine-tuning what we could build based on getting a kind of good fiber layout with kind of a suite of kind of fiber layout tools and simulation tools as well. So here you can see some of the design development, but what was important is that this robot, for example, was built entirely from scratch. So there's an interesting kind of trade-off. On the one hand side, we can have robots that are taken from industry or are appropriated from other contexts, and they lower the kind of difficulties in programming them, and we can get them up to speed and working. On the other hand, there might be functionalities that we need for construction. So being able to develop a kind of proof of concept drone just for moving a piece of fiber back and forth at a very kind of high, somewhat reasonably high tension was basically widely expanded the design space. So I think working back and forth between off-the-shelf or already known industrial tools versus developing custom hardware, being able to work back and forth between those two types of machines becomes very kind of advantageous. And at the same time, we have to develop more supporting hardware. So in this case, we developed a kind of custom tension mechanism that would basically actively extrude when the drone was flying, so the drone didn't have to pull all the fibers. But at the same time, when the robot was kind of winding, the tension mechanism would have a kind of active weight, which is called a dancer bar. So the high weight would guarantee a kind of high tension on the winding. So here you can see the whole process. The drone is using a kind of April tag-based localization strategy. The whole process is basically achieved because this kind of end effector, which is a tube, is basically exchanged in between robot and drone. So on the drone side, it can grab the end effector by electrostatically activating a magnet. And on the robot side, it's just a kind of pneumatic gripper. So through this kind of set of hardware mechanism that had two different kind of attachment points, we can really achieve multi-robot collaboration. So here you can see after it grabs it, it finds it with an IR LED. It moves the relative transformation. Then it moves around the frame and winds the point. So actually, in comparison to some of our other fiber winding projects, which you might have seen, or you can check out from the ICD website, this is actually a very inefficient process. But the innovation here was really in the kind of multi-robot collaboration and the kind of high-level control strategies. So to organize this whole project, we had this kind of custom design tool where we took a kind of target syntax and we compiled it into a sequence of steps that needed to be executed each time. This is called a task list. And this task list would basically be loaded, and then it was a little bit like baton trading. So it would send this patch of tasks to the robot would execute that task, and when it had finished its task, it would report back. So this is basically how we kind of orchestrated the kind of multi-agent communication during the project. So what's also important is that here we were also using ROS. So ROS is a kind of state-of-the-art robotics middleware. It's based on publish subscribe, so this is very scalable and it's very interesting. I mean, the main challenge here is how you make a CAD design environment, and the ROS based tools, how you kind of make them compatible. And this is a big challenge, I think, for kind of future developments, is how we take these domain-specific tools and these domain-specific libraries with functions and really develop kind of ways that they can be integrated and interface with one another. And here, of course, we also had to develop a kind of workflow for the online and adaptive control code. So here the robot is running some code. It basically has a set of subroutines, which might be winding, it might be gripping. Whenever it gets a kind of package of data, it says, oh, what data package did I get? They'll tell it what task to run. If it's a different task than what it had previously run, it will say, oh, I want to run task 50, therefore I'm going to be moving around the platform. It executes that task, and then the kind of control loop iterates until it gets a new task. So in the end here, we also produced the kind of large demonstrator. As I mentioned earlier, it was a very inefficient process. So laying one fiber, for example, could take up to 5 to 6 minutes. So we realized that the drone in this case, even though the kind of communication platform was very robust and very interesting and a huge kind of accomplishment, the drone is not the perfect solution for the kind of high tension collaboration. So something more like a cable-driven kind of system would make more sense. So that's something that we looked into in kind of follow-up studies. So here you can see some kind of load tests. So for example, actually with the drone process, we actually ended up, because it was so much faster, doing many of the parts of the moving the end effector back and forth actually manually. So this became much more fast. and much more efficient, which becomes an interesting question of when do you plan strategically to include humans in the fabrication loop and enable them to intervene. So this is an open point of development and something that I think is quite interesting. And of course, here are the students. This pavilion is still usually, I think it's on display. I think it's probably in ZKM. I'm probably just going to skip through this last project and kind of wrap up quickly. Okay, so I just want to kind of end with a few different thoughts for how we kind of pursue robotics in construction, how we kind of can think about how we can actually make robots in the construction site and robots building buildings and new structures a viable reality. And I think what's very interesting is to actually see these kind of way that this is sometimes approached in actually robotics. So here, for example, is one of my favorite projects to show, which is the moon landing equivalent for robots, which is assembling an Ikea chair. So the video here is very painful to watch. The robot, I think there's better videos of this, but basically, you know, Ikea chairs have been developed from a very specific logic of assembly, which is basically the logic of human dexterity. So trying to watch a robot trying to do something that was developed from the perspective of manual assembly is very difficult, because ideally we want to redesign chairs and we want to redesign buildings and building structures to really unlock the kind of potentials or to enhance the ability of the robot to actually do its task. So we really need to approach this from a design perspective. So understand the limits of the robot and to develop new kind of systems that will really enable us to actually enable robots to construct with the kind of sensor capabilities that they have at their disposal right now. Then the next question is really, how do we incentivize domain-specific tools? So what does a construction robot look like? We shouldn't, for example, appropriate industrial robots. We should try to incentivize fundamental research on what a generic construction robot could do that could execute many different tasks. And maybe hybridize it in a system with also very task-specific robots that we saw not only in Japan, but also, for example, in some of the earlier robotics projects that I showed. We should really think about this not in terms of a process where you take the robot and then you develop the building system, but we should really think about this as an integrated design process. So as I showed in the kind of second project, the tooling, the material, and the built system, and then the robot that's building that project all need to kind of co-inform each other. So it really shouldn't be a linear progress. And then the next question is really accelerating accessibility. How do we as an industry address the lack of interoperability? So one great initiative actually at the ETH Zurich, which was initiated by the Block Research Group, but now also kind of initiated across many different ETH groups, but also a lot of different universities worldwide. It's basically a kind of framework for platforms for research that are non-proprietary. So how do we develop code that you can kind of integrate to all of these kind of systems? And in fabrication, of course, the kind of hardware, software integration is a key aspect to future development. So this is something that's open source. So of course, this maybe could be a topic of development and workshops in the future for AEC hackathons. And here's just a kind of different front ends and back ends that Compass currently supports. And then of course, as the kind of research institutes that I'm currently have been lucky to be affiliated with, we also have to really approach these questions looking from academia, but also looking at industry and practice. So it's really about how do we kind of combine the interests of both and co-inform each other for the future of the field. So that's all that I had today, and so I'm going to probably stop sharing, and then you can feel free to ask questions.